we're looking at graphs of functions and derivatives. This is not a section that's in your book, so be sure you take good notes because there's not really any other place to get to this. But it's a pretty simple lesson, but with a lot to it, as you'll see over the next couple of days. There's a lot of implications from this. As we look at this, our objective is to analyze graphs of functions and or their derivatives. We want to use information on the first derivative to help sketch graphs, and we want to use information from the second derivative to help shape the graphs so that they're not just always kind of up, down, or looking like absolute value graphs. Okay? So, first derivative. A function's first derivative tells how the function rises and falls. I put this great big kind of massive graph here where you can see it's got endpoints. So you have an absolute min over there on the left because that is the lowest point of the entire graph. You have a local min on the right because it is going down, but it's not the lowest point. The lowest point was back at A. As you can tell, the graph starting from the left, from that absolute min, from your A value, if you go up, your slope on this is always going to be positive. As I go here like this, my slope is always going to be positive right in through there. That's where I get the f prime is greater than 0. That means my function is increasing. Okay, at this point right here, sorry my pen is not great, but at this point right here, then right there, just that one point, my slope is 0. My slope is 0, which means I have a horizontal tangent. We know that's a saddle point. Continuing on from there, I am continuing to increase. My slope continues to be positive. At this point again, sorry, my pen is way off. Okay, and I stopped and recalibrated, so maybe it'll be a little bit better. At that point again, I have 0, but this time on the other side of it, I'm coming back down. Now you can tell that your slope is negative, and so that first derivative for any point in there should be negative, should give you a negative value. Your function is decreasing. Again, right here, I've got horizontal tangent 0, local min, it says. These were local maxes. This over here was no extreme, okay? So it's neither increasing it's neither a max or a min there. However, I do want to point out before I go any further that from A to this C2 value, that is considered to be increasing on that entire interval. Even though you have a horizontal tangent at that point right there, it is still considered increasing because the points to the left are lower than the points to the right on that. So it is considered to be increasing at that. The y values to the left are considered lower than the y values to the right. So this comes down, again, a local min, you know this, we're coming back up. Now right here at this point something happens in that f prime is undefined. You know as well as I do that if you've got a cusp right there, then the derivative doesn't exist. And so that's what happens there. However, you know, that's still going to be a max. And in this case, because it's the highest point on the graph, it's an absolute max, isn't it? Okay. From there, we're starting back down again. So slope is negative. Slope is 0 right there. And then slope continues to be negative. Again, this right here is a saddle point because it continues to be negative on either side. My derivatives are both negative. So that's where that comes in. Okay. As you look at this, maybe I should put it up here. So if f prime equals 0 at maxima and minima and saddle point, how are we going to determine what's happening? Okay, well that's pretty simple because we're going to have the signs changing. Right here, f prime equals 0. I'm changing color so you can tell. Right here, f prime equals 0, but to the left, these were both positive. The signs didn't change, so therefore I knew it had to be a saddle point. However, right here, where f prime equals 0, to the left I am positive, and to the right I am negative. And so therefore I know when my signs change like that from increasing to decreasing, from positive to negative, that had to have been a max. This right here had to have been a min. because I changed from negative back to positive, decreasing to increasing, so it had to have been a min there. Okay, so that's how we decide. Okay, so let's take a look at our first derivative test. To use your first derivative test, in order to classify points, what you want to do is take your derivative of your function, set your numerator and denominator equal to 0, and notice I did say and the denominator. That's a big deal, okay? Set them both equal to 0 and solve for x. The reason you set the denominator equal to 0 is because of that point that you had that was a cusp where the derivative didn't exist. That's going to let you find that point as well and be able to test on either side to whether it's still going to be a max or a min. Those points like that are called your critical points. And you need to know that. That is always where f prime of x equals 0. Okay? Critical points where f prime of x equals to 0 and then solve for x. You're going to fix a number line with those points and then substitute values to the left and the right of each into the derivative equation in order to determine the sign. Okay, let's say that, we go through, we get our critical points, and we have a single critical point that has a value 2. I want to take something to the left of 2, like maybe 1, and something to the right of 2, like 3, and I want to plug those into f prime. And I'm going to, when I do this, I will always label my lines like this with an f prime. To check the sign, I don't care what the number is when I plug into 1, but I do care if it's positive or negative. I don't care what the number is when I plug it into 3, but I do care if it's positive or negative. If it's positive and the negative, then I know that I have a relative max at x equal 2. Okay, and so we're worried about the signs on these. If the signs change from positive to negative, relative max. If negative to positive, relative min. If the signs remain the same when I do this, if I had put in a value of 5 and I get negative and negative on both sides of it, then what I know is that I have a saddle point and my graph is continuing to decrease all the way through that point. Okay, so pretty easy there, not a problem. Pulling this out right here. Okay, don't forget, if your function is bounded, it has a left and a right closed endpoint, then you need to also check your endpoints in order to find absolute extrema. The very highest point is your absolute max, the very lowest point is your absolute min, and it is possible to have more than one absolute max if you have two x values that give you the same y values. Same thing with your absolute min. Okay, first derivative test. For the function f of x equals x cubed minus 12x minus 5, use your first derivative test to find the local extrema. Okay, we said what you need to do on this is to find f prime of x, 3x squared minus 12, and set it equal to 0. When you do, you're going to get x squared minus 4 equals 0. When you factor 3 out and divide it, and so x equals plus or minus 2 for that right there. These right here are your critical points. Okay, that was where your first derivative equaled 0. So what I want to do from there in order to find local extrema is put these on a number line. Negative 2. Positive 2, and plug some values in. Okay, I'm going to plug in something less than negative 2. I'll plug in a negative 3. Plug that into f prime. Okay, so when I plug that into my derivative equation, plug in negative 3, then I'm going to get a positive minus a negative. So plugging it in, I'm going to plug it into this equation right here. Okay, and so I've got 3 squared is 9 times 3 is 27 minus 12. That's going to be positive. Something in between, I'm going to say I'm going to plug in a 0. So 3 times 0 squared minus 12, that's going to give me a negative. Something bigger than 2, say 3. Well, I know from the other that that's going to be squared, so it's going to give me a positive. So this is going to be an increasing to the left there, decreasing to the right of negative 2, back to increasing to the right of positive 2. So I know that what happens is that at negative 2, because it went increasing to decreasing, I have a max right here. Now just a relative max, not an absolute max, because this one's not bounded, and I'm not worried about it if it's not bounded on the left and the right. Because this one was going decreasing to increasing, then this one right here is going to be a min. Now then, to find my values, the actual points where that happens, I need to plug those values back in to my original function, f at 2 and f at negative 2. Okay? When I plug 2 in, I have 8 minus 24, sorry y'all, minus 5. Okay, so negative 29 at 8 is negative 21. F at negative 2 in there, I get a negative 8. And then plus 24 minus 5. So I've got negative 8 and 24 is 16 minus 5, which is 11. And from there I can see that the point 2, negative 21 is my relative min, while the point negative 2, 11 is my relative max. So pretty easy. Not a big deal, and it's nice. It helps us graph. All right, let's move on. Second derivative. Second derivative of a function defines its concavity or its shape. If the second derivative is positive, the function's concave up. If it's negative, then it's concave down. So right here, my second derivative would be less than 0 because it is concave down in this space right here. Okay, to the right of that, my second derivative would be greater than 0. Okay, because it's concave up. Notice from the graph that if the tangent line lies above, like these do right here, then the graph is concave down. If the tangent line lies below, like these right here, then the function is going to be concave up. That's always the way that it's going to work. Okay? Moving on, see if we can put this to good use. The point where a function changes concavity is called the point of inflection. It's found by setting the second derivative equal to 0 and solving for x. So f double prime of x equals 0. Okay? Oh, and I should have said equal to 0, both the numerator and the denominator. Okay? So numerator and denominator. Numerator equals 0 and denominator equals 0. Okay, so it's where f prime equals 0 or is undefined. Sorry, kind of bad notation here, but jot it down. Configuring, it's still found by configuring a number line and checking the signs on either sides of the values. It's found in part 1. So again, we're going to fix a number line, but I'm going to do a second derivative like that. And we're going to plug in our values on it. Let's say that I get a positive right here and a negative right here. Then what I know is that to the left of this value, whatever it might be, well, let's put in a 0. This is going to be concave up, and this is going to be concave down. Okay? The signs change, then the concavity of the graph changes as well. Okay, sorry about that. And then what I wanted to get in right there is that point where it changes, that's that point of inflection. Where the signs change like that, sorry. That's your point of inflection. Now, here we go. So I'm going to sketch a graph of the function f of x equals the cubed root of x. So that means that f of x equals x to the 1/3 power. So then f prime of x equals 1/3 x to the negative 1/3, 2/3 power, right? And on that right there, now I'm beginning to see where, if I rewrite this, I have 1/3 x to the 2/3, and I can begin to see that on this one, setting my numerator equal to 0 doesn't help me. Okay, setting my denominator equal to 0 is going to give me a little bit of information here. When I set the numerator equal to 0, I get nothing out of it. Okay, so I know that there's not really a max or min on this one. When I set my denominator equal to 0, 3x to the 2/3 equals 0, and go through and solve, I still get x equals 0. Okay, well, let's figure out if we've got a cusp or what's happening here. So at 0, I'm going to put that in. This is, again, an f prime line. Let's plug in something to the left of that. Let's say that we're going to plug in a -1. If I put a -1 into my first derivative, the cubed root of -1 is going to be a negative, squared is going to be a positive, and times 3, so that's going to be a positive value. And then if I plug in a positive 1, since I've got a cubed root squared, no matter what I plug in, I'm going to get a positive value. So that means my function is increasing no matter what. That's my first derivative. Okay, so I know I've got something going on there. It's not a saddle point because my derivative wasn't 0. Okay, but I've got some sort of vertical tangent line going on there that's going to affect my graph in a funny way. Let's do our second derivative. Get our concavity going so it can help us with our graph. So I've got the second derivative of x. That's going to bring down the -2/3 times the 1/3, so that's going to give me a -2/9 times x to the -5/3 when you subtract 1 from it again. Okay, well, again, I've got, -2 over 9 x to the 5/3. Setting the numerator equal to 0 is no help because that doesn't happen. Okay. Setting the denominator equal to 0, though, I end up 9x to the 5/3 equals 0, which again gives me 0. Okay, so I'm still looking at 0. 0 is a pretty important point. We knew it was a critical point from right here. Second derivative, from the first derivative, the second derivative tells me it's going to be important, but it's not called a critical point there. We're still going to have 0 like this. This is going to be my second derivative line. Plug in something to the left, let's say a -1. When I plug that in to my second derivative right here, okay, then that does something completely different. If I plug in a negative, the cubed root of a negative is negative. Negative to the 5th is still negative. I have a negative on the top. So negative over negative gives me positive. And I know that my graph should be concave up on that right there. If I plug in a positive 1, the cubed root of 1 is 1. 1 to the 5th is still 1 times 9. That's a positive. But -2 over positive is going to be a negative. So my graph is concave down right there. Okay? So when I start to graph this, and it looks like this right here, the only critical point that I've got is this 0 right there. I know that it is increasing on either side, but it's not going to be a line. Okay? I've got x to the 1/3. And so I don't know exactly what that looks like, but it's not going to be a line because of my concavity. It's got to be concave up on the left of it and concave down on the right. Okay? So I need to be coming in, concave up like that, and I need to go out with it concave down. And so that's how that second derivative helps us shape that graph. The whole graph is increasing all the way from the beginning to the end, but the concavity changes there at 0. Also at 0 right there, if I were to go up and down and draw a tangent line right there, that tangent line right there is a vertical tangent line. And so that's why my first derivative came out undefined. Okay. We want to put down a helpful diagram, and this will be the last thing that we do. Okay. Concavity has to do with my second derivative, so I want to be sure that I know that this going this direction. It all has to do with the second derivative. Right here, my first derivative is going to be going this way. All right, if I have something increasing and concave up to where both things are positive, it's increasing and it's concave up, then my signs are the same. And we know from doing this earlier, if my velocity, which is my first derivative, and my acceleration, which is my second derivative, have the same sign, then I'm speeding up. This curve looks like that. And you know what? If I'm following that right there, you can tell I am speeding up. It's getting bigger faster. Okay? When I move to the right, and I'm looking at it being increasing, but concave down, okay, I'm still climbing, but I'm facing a different direction. And you can tell that, as I start that, I'm going pretty fast, but as I start getting up here, I start to slow down, don't I? And we know that different signs mean that I'm slowing down. Okay? If I have negative for decreasing from my first derivative, but positive for concave up from my second derivative, then I'm decreasing, but it's still a concave up situation. Okay, well, what does that look like? Okay, decreasing, but concave up. Well, that looks like that. Okay, I'm going down, but I'm going to be slowing down as I get to the bottom of that. Now, decreasing but concave down, that's going like this. And you can tell if I followed that, I would be going down in a hurry. Okay? So that's how you get speeding up when your signs are the same and slowing down when your signs are different. That's also what those curves are going to look like and what you need to be thinking through whenever you see those different signs like that. All right, that's pretty much it. We're going to look at deciphering graphs tomorrow and hopefully be in good shape. Y'all have a good evening. Bye. Bye.